These are the solutions to recitation activity 7. The boiling of water, so it's liquid to gas for water, is an example of this would be endothermic. We have to add water or add energy into the liquid water in order for it to boil. So it's an endothermic reaction, and the Q of the reaction should be positive. So again, endothermic because liquid water has to absorb heat in order to boil. Which statement is true when 4.75 grams of magnesium reacts with excess oxygen? If I had 2 moles of magnesium, then 1,204 kilojoules of heat would be given off, would be released by this reaction. This is an exothermic reaction, so energy is being released by this reaction. But now when only 4.75 grams reacts, not quite 1,204 would be given off, so I'm going to calculate my Q reaction by taking 4.75 grams of magnesium. It's 24.3 grams per mole of magnesium. And then I can use the coefficient here for every 2 moles of magnesium according to my reaction that reacts. Then there's minus 1,204 kJs of heat change that accompany that reaction. So I go 4.75 divide by 24.3 divide by 2 times negative 1,204. So the reaction is hold on one second, 4.75 divided by 24.3 divide by 2 times 1,204 negative okay, let's put in the calculator wrong the first time, so I get 118. So my Q reaction is negative because the reaction's losing heat, giving heat off. So I have 118 kilojoules released. Question 3. We have ammonium nitrate dissolved in water, according to the reaction below. Endothermic, so the reaction is absorbing heat. The heat would come from the solution, so the solution temperature should decrease. So the temperature of the surroundings here will decrease because the heat of the reaction is positive. So if the heat of the reaction has to go up, then it has to come from the surroundings. The solution is the surroundings. So the solution temperature should decrease because the reaction absorbs heat from its reactants. Looking at the choices, the solution drops in temperature because the reaction absorbs some of its heat. So B looks like the best answer. The temperature of the solution should drop because the reaction absorbed some of its heat. The solution temperature does not drop because the reaction released some of its heat to the product. So this just makes no sense. So B is our best answer. 4, what is the sign of delta H for the following reaction, given the following? So I have water goes to H2 plus a half O2 is what I want to know. I have 2H2 plus O2 goes to 2 water is minus 483.6. So I got to flip the reaction. Delta H of that reaction would be plus 483.6. I have to cut all the coefficients by half. So I cut the delta H by half. So it should be 241.8 positive. So we have iron and aluminum in equal masses at 100 degrees, which would lead to a greater temperature change when added to water. So which one's going to lead water to increase in temperature by the most? So aluminum with the same mass is going to have more heat to lose than iron because it has a higher specific heat. It's like if we took water, which has an equal specific heat, if we took, imagine we take even higher CS. We're going to lead, say, water at 25 degrees versus water at 100. If we took equal quantities of water, we'd end up somewhere, right in between there. So we'd basically end up with the average of 25 and 100. Well, if we take an equal mass of aluminum, the problem is that not as much heat had to be absorbed by the aluminum in order for it to increase its temperature compared to water. But more heat would have been absorbed by the aluminum than iron. So aluminum has more heat to lose. So the aluminum is going to cause the greatest temperature increase. Both of them would cause an increase in the water temperature. Nothing's going to decrease the temperature of water. So the temperature of water has to increase. You put something hot into water, colder water, the water has to go up in temperature. Its aluminum is going to cause it to go up by more. Now, there could be some confusion here. Like maybe if you're heating up your sample of aluminum and iron, the aluminum sample is going to take longer to heat up, but at some point it gets to 100 degrees. Imagine you put iron into like a test tube, you put aluminum into a test tube, and you put those test tubes into a boiling water bath. At some time, it might take longer for the aluminum to heat up, but aluminum, once it gets to 100 degrees, you pour it into the water, it's going to make water go up by more than the iron would. A 12-gram sample of cesium hydroxide, which is kind of funny. That would correspond to almost half of the cesium that exists on Earth. So not a practical problem. Anyways, 12-gram sample of cesium hydroxide dissolved into 125 grams of water in a coffee cup calorimeter. The water in the compound initially at 25 degrees C. What is the temperature of the solution following the reaction? We're given the specific heat of the solution and that we're in a good insulated calorimeter. So what this tells us is the Q reaction is a negative Q of the solution, the negative Q of the surroundings, which is the solution, negative MCS delta T for the solution. And then the Q reaction, we can calculate it from delta H. So the Q reaction for specifically 12 grams of sample would be, I'm looking here, minus 71.55 kJs per 1 mole of CSOH. And so my Q reaction, I'd be taking the 12 grams of cesium hydroxide, 149.91 grams per mole, and for every mole, minus 71.55 kJs. And then my CS is in joules per gram Kelvin, so I'm going to go 1 kJ, 1,000 joules. So this is my Q reaction in joules. So this is going to be 12 divided by 149.91 times negative 71.55 times 1,000. So this is negative 5727. Not kJs, just Js. We converted to joules. And so this is the Q reaction here. That number of joules is equal to negative mass of the solution. This is how we know this is the solution. And the solution would be 137.0 grams times 4.184 joules per gram Kelvin or degree C. Let's leave it Kelvin. And then times delta T. Let's solve for delta T. So keeping these minus signs, exothermic reaction, the temperature of the water should increase, right? The temperature of the solution should go up because of the exothermic nature. Our delta T is going to come out to be positive. So delta T, 57.27, negative divided by negative 137, divided by 4.184. So my delta T, solving for this, is 9.99 Kelvin. And so now, again, I want to make sure that we're not too confused with Kelvin here. I've done this a couple times in class now. But our delta T is 9.99 Kelvin or 9.99 degrees C. I'll think of it this way. Let's let's do it the long way. Like, let's say we're going here and we're saying, all right, my T final minus T initial is 9.99 Kelvin. And then I know my initial temperature is 25.00 degrees C. And so therefore I'm going, and that's 298.15 Kelvin. And so I do 9.99 plus 2.98 Kelvin, or 298.15 Kelvin. That's 308.14. And then we subtract 273.15 to go back to degree C. And of course, 273.15 subtracted is 334.99 degrees C. It's a long approach, right? To say 9.99 was the Kelvin difference in temperature. We converted our initial to Kelvin, and then we solved the algebraic problem to solve for TF, and then we converted back to degree C. Lengthy approach. Well, if we had made this realization here that the delta T is 9.99 degrees C, then you can see that TF minus TI is 9.99 degrees C. So the initial plus 9.99 is 34.99 degrees C. So you can see degree C, Kelvin, and a difference in temperature are synonymous with each other. Okay, so number 7, we have a capsule charged with a certain number of moles of CH4, definite excess of O2, placed into a water bomb calorimeter with a total heat capacity of 9.245 kJs per Kelvin. What's the heat of combustion in kJs per mole? And the calorimeter temperature increase is given here. So our Q reaction, negative Q of the surroundings, which is the calorimeter, described by a C cal and a delta T. We show our units here. We go minus 9.245 kJs per Kelvin, and then times our delta T, which is final minus the initial. So that should be 6.019 degrees C. I'm intentionally canceling this. This is perfectly fine. The difference in temperature, if we convert to Kelvin and take the difference, would be 6.019 Kelvin. So Kelvin and degree C and delta T's cancel. That's fine. And so the reaction occurring in the calorimeter has a delta H, or a Q reaction, of negative 55.65. And then we just have to divide by the limiting reactant. So we put the limiting reactant, which is the 0.0625 moles of CH4. If we're not sure, we're just looking at the combustion reaction takes place in the calorimeter. And so CH4 plus 2O2. So clearly oxygen's in excess here, and CH4 is our limiting reactant. And so if we divide by 0.0625, we get 890 negative, so minus 890.3 kJs. Question 8, the standard enthalpy change for this reaction here, using, this is Hess's law. And so for this problem here, what I'd be trying to do is just start with a reactant or product that's only in one of the reactions first. Is usually the easiest starting point. So I only see NO2 here. I don't see NO2 anywhere else. And so I know that this reaction here needs to be flipped to get NO2 to the reactant side. So you multiply this by minus and then 3 halves. 3 halves so I can get 3. So if I do that, it's going to be 3 NO2 goes to 3 NO plus 3 halves O2. Delta H for this being minus 114 times negative 1.5 is 171. Delta H is in kJs. And so let's see what else. HNO3 HNO3. HNO3 is a no other reaction, so I gotta keep this reaction in the same direction, but cut everything in half. So I gotta go N2 plus 5 halves O2 goes to 2 HNO3. My delta H here, I have to cut this one by half. Negative 255 times 0.5 minus 127.5. And then the final reaction must just be one that's going to help me balance out a few other things. Let's see. So like NO is here. NO is here and nowhere else. No, actually NO is also here. But we have too much NO right now. We only need one NO and we have 3. So what if I flip this reaction here and put 2 NO over here? Goes to N2 plus O2, so I've just done a simple flip. So this is minus 181 kJs. And now how do these add up? Let's imagine we add up these reactions. I'd have 3 NO2 plus N2 plus 5 halves O2 plus 2 NO goes to 3 NO plus 3 halves O2 plus this plus all that. Well, what's canceling? What's on both sides of the reaction in identical quantities? N2's on both sides and cancels. I have these O2's here, so 3 halves plus O2 would be 5 halves, and 5 halves. So those cancel, and so I'm left with 3 NO2. Oh, I forgot to write a water somewhere. So I forgot to write this water in here when I cut this in half. So I just neglected that water here. And then these NOs, 2 of them cancel with all but 1. So we leave an NO behind, and so that's going to be 2HNO3 plus NO, our desired reaction. So it's just like a puzzle. Like, how do I need to manipulate those reactions so that I can add them up? And then once I see that, then I know I just add up these delta H's. So I go 171 plus negative 127.5 and then plus negative 181. That's minus 137.5. Call it minus 138 kJs. Question 9. Using standard enthalpies of formation. So the delta H of reaction is just the sum of the delta HFs and the products, accounting for stoichiometry, minus the sum of the delta HF and the reactants. And then anytime we have a substance in its elemental form, delta HF is exactly equal to 0, and we have to be able to recognize that. So I'm doing 3 times CH4 plus CO2 plus 2 times liquid water minus 4 times CO, and that's it on the reactant side. So I'm going to do 3 times minus 74.85. The way this works is it's 3 moles times the 74.85 kJs per mole plus CO2. So 1 mole times negative 393.51 kJs per mole. And then plus 2 times liquid water, making sure to use liquid, not gaseous water, although gaseous water is not given. But 2 times negative 285.85 kJs per mole. And again, that's 2 moles times, so the moles canceling. So this is the sum of my reactants here. And then minus the sum of the products, which would just be 4 moles times CO, minus 110.54 kJs per mole. So 3 times negative 74.85 plus 1 times 393.51 plus 2 times negative 285.85 syntax error. Let's see. Let's just do it again. So 3 times negative 74.85 plus negative 393.51 plus 2 times negative 285.85 and then minus 4 times negative 110.54. I get minus 747.6. So I'm just very meticulous. I do 3 times, and I type in the negative, and I do plus, and then put in the negative, and I do plus 2 times the negative. So I just try to be very direct with the way I do the calculation. I do minus, and then 4 times negative. I try not to do the math in my head. I try not to look ahead and be like, okay, this becomes plus with the double negative, because that gets to me to be a little too confusing. So I just try to put the numbers into my calculator exactly as they are in the calculation, so that I hopefully don't make a sign error. Question 10, bond strength. So bond strengths are just a little bit weird. We're going to try to see in this type of question here, how much energy does it take to break these bonds? And so our delta H, and this becomes an approximation, is the sum of the bond strengths but in the reactants. This is a weird one, minus the sum of the bond strengths in the products. This just really stems from Hess's law, that we're just saying, well, how much energy does it take to go to 2N plus 4 H's? It should take energy to break those bonds. So we take the bond strength 941 times a mole, and we take the 435 kJs per mole. We got 2 moles. So I do 435 times 2 plus 941. So it takes, and it goes uphill, plus 1,811. I can't write. 1,811 kJs to break those bonds. So how much energy do we get back when we make the new bonds? And so I'm making 4 NH bonds and an NN single bond. Okay, and so then we're getting energy back. I can look here and try to say, okay, these are NH single bonds. I'm making 4 of them. So I got 389 times 4, and nitrogen single is 159. So these bonds here, to break all those bonds, would take 1715 kJs in the products, but we're getting that back because we're making those bonds. So we go 1811 up and then minus 1715 downward. And so that ends up being plus 96 kJ. So this is an endothermic reaction, is what it results in being here. So it's just the sum of the bonds it takes to break the bonds in the reactants minus the energy you get back when you make the new bonds in the products. Always takes energy to break bonds. We always get energy back when we make the new bonds. Oxidation number review. So sodium's a plus. Our ions are the same charges that we've come to expect. So carbonate's a minus, hydroxide's a minus 1. And so if we go minus, 2 minus, so we got 2 of the minuses and a 2 minus, making this entire thing here, which makes sense with a plus, be negative charged. And so that means aluminum has to be a 3 plus. So I'm just looking at the charges of these polyatomic ions. That carbonate's a 2 minus, hydroxide's a minus. I got 2 of them. So that is an overall 4 minus. And so if I have a 3 plus on the aluminum, that makes the overall group of these ions here overall negative, which makes sense with the sodium positive. So kind of a tricky oxidation number question, but just a review question from chapter 4. Another review question from chapter 4. We have 2 liters of silver nitrate, 1.25 liters of calcium iodide. How much precipitate forms? This is just like a stoichiometry problem, but using topics from chapter 4. And so let's do this math here first. 2 liters times 1 mole per liter. This is 2.00 moles of AgNO3. And then 1.25 liters of 1 molar calcium iodide, that's 1.25 moles of calcium iodide. So I have 2 moles here, and I have 1.25 moles here. And if I consume all of the silver nitrate, I need 1 mole of calcium iodide to react with it. But if I were to consume all the calcium iodide, I need 2.5 moles of the silver nitrate. So this is my excess reactant, and then the silver nitrate is my limiting reactant. It's one that goes to 0. So I should be making, if I'm losing all 2 moles, going down to 0, my X would be equal to 1 mole. So we should be forming 2 moles of AgI. And so how much precipitate forms? 2 moles of AgI. Question 13. This is actually, no, wait, this isn't my question. So how much this solution do we need to fully neutralize 2.87 grams of calcium hydroxide? Molar mass given here. And so this is just a stoichiometry problem. Number of milliliters of the HCl solution would be equal to, let's start with the given quantity of the other reactant. So it's going grams to mole for calcium hydroxide. For every 1 mole of calcium hydroxide that's present, we need to add 2 moles of HCl. And then we're adding HCl where it's 0.819 moles of that solution per liter of the solution. And a liter is 1,000 milliliters. So if I go 2.87, divide by 74.1 times 2 times 1,000, divide by 0.819, I get 94.6 milliliters. All right, so a little bit of chapter 4 review here at the end of this activity. All right, that's all for activity for this activity. Thanks for the attention.